Okay, again, thank you very much for attending the meeting. I'm sorry for the problem we had with the invitations earlier on. So let me start. A lot of what I'm going to say today is actually feedback from our end users who have been using these systems for a couple of years. And they tell us that the imaging systems that we provide give them quite a few advantages, and these are what they say. The first one is that by monitoring the temperature throughout the glass tank in the radiometric thermal image, you're able to measure multiple temperature points, and within those multiple temperature areas, you're able to trend temperatures, measure important areas like the crown of the furnace, the areas at the tops of the ports, the port arches. And by doing this in a repeatable way, you're able to predict and prevent damage to the refractory materials and extend the campaign life of the glass tank. The other thing we're told also is that we're able to detect the temperature of the blanket and also visually see within the thermal image where the blanket, the batch transit line is. We're also able, because this is a near-infrared device, to view the flames and to tune burners by viewing the flame propagation, and also if there are any issues with burners as well. So within glass container plants and fiberglass plants or float glass plants, they all share this common thing of a glass tank. The glass tanks can be different sizes depending on what you're producing, and they are usually either cross-fired tanks or end-fired tanks. But most of what is necessary for measurements in here is common throughout all of these. Usually the tank is fired from one port to another, or from one set of ports to another set of ports. And as this is happening, the exhaust ports have regenerative brickwork behind them that stores the heat from the waste gases. And then after around 20 minutes, a reversal happens. And now what was the exhaust port now becomes the charge burner port. And the incoming air is preheated by that stored energy in the regenerative brickwork. So here we see a schematic of a typical cross-fired glass tank. Regenerators both sides, ports alternated between firing side and exhaust side. And typically, one of our near-infrared Borescope imaging cameras is placed high and centrally on the bridge wall, looking up the glass tank at both the refractory brickwork and the glass itself. So here we've got a schematic of a typical installation, and here the customer has mounted the thing high in the bridge wall, looking downwards at an angle towards the glass and towards the burner ports. And it's here at the tip of the lens tube. So our lens tube goes through a very small hole in the wall of the tank. And the tip of the lens tube is protected at this angle by having a brick cast which has a slight angle on the inside. That's just so the tip does not protrude into the gases of the furnace itself. So the tip is usually recessed around 5 millimeters into the refractory. The view from the end of this lens is a 90-degree wide view, so you see a lot of information inside of the glass tank. On this side, we see a photograph of a unit actually installed, again at this angle looking downwards, and it's installed on an optional auto retraction mechanism. That auto retraction mechanism will sense if there's a loss of coolant to the system or a loss of purge air or an over temperature situation at the lens tip. Okay, and on any of those conditions, that auto retract system will automatically pull out the imager to prevent damage, and as that imager retracts, there is a shutter which closes the port. So here we see a scene inside a typical cross-fired glass tank, and as you can see in here, we have on our thermal image, we've selected a monochromatic palette. Some people prefer that monochromatic palette. And one can see that currently the tank is being fired from the right side, and the ports on the left are currently the exhaust ports. You can see the glass within the tank. You can also see the mat, the batch mat floating on top of the tank. And this particular customer has set up profile lines, and these last two profile lines are really to catch the fact that the melt has completed and that batch is now homogeneous within the glass itself. You can also see that they've placed a multi-segment profile across the crown, and this multi-segment profile across the crown shows the temperature profile across the furnace, and this is displayed in here. You can also position anywhere on that profile, and it will show you a line on this temperature profile of where you were looking. So now the next image is one where we've set the color palette in a color. Okay, this is an Infired tank. So very similar to what we saw before, slightly smaller than the one we saw before. And in this particular case, you can see that the tank is being fired from the left-hand port currently. And so the burner is coming in here. The exhaust gases are swirling around and coming out of this port, which is currently the exhaust port. And in this case, the customer has selected an area of interest in this image, which you might see here in this green rectangle. Okay, and they've selected the function of that area to be a minimum temperature within that area. And you can see here in that area that it is 1446 degrees Celsius. So that's the lowest temperature in that area. Now we have the very same glass tank being viewed when it is being fed from the right side burner port now to the left side, which is now the exhaust port. The same area of interest is being shown, and it's calculating on the minimum temperature. And first of all, you might see in the image that it does look slightly darker down here, but also the temperature has gone down by almost 100 degrees Celsius, purely as a matter of from which side the tank is being fired. And in this particular case, they found that when they were firing from this side and exhausting from this side, they were pulling a slightly negative pressure at this side, and there was a structural crack within the tank that was pulling in colder air. And they didn't realize that they had that structural crack there, and they were able to detect it, to understand it, and to do an early repair on it before it became a more serious issue. So now let's look at refractory temperatures themselves. And some of the areas within a tank that are very, very critical are the ports themselves, the areas around the ports, and particularly the tops of the ports, known as the port arches. And so here we can see on a newly lined furnace, this is an Infired one, this is typically the area that would be measured on a reversal, sometimes using a portable infrared thermometer. The difficulty in making this measurement, though, is that you have to be certain to make that measurement exactly the same amount of time after the reversal starts, because the temperature of the refractory can drop very quickly, many degrees per second, during that reversal. So it's very important, if you're going to trend these temperatures, that you make the measurements at exactly the same times. Okay, so with this in mind, here's a thermal image of another Infired glass tank. It's another customer. And in this particular case, they have set up 4 areas of interest within the scene. The first 2 areas of interest here are at the port arches. Okay, and you're able to record these temperatures live, and you're able to trend them, and you're able to replay them. So you're actually able to replay them and stop them at exactly the same point in time after each reversal and match temperatures very well, rather than thinking, oh, I'm not quick enough to start measuring temperatures. Okay, so you can see on the firing port in this area, they've got a temperature of 1509 on the port arch. And on the exhaust port currently, they've got a temperature of 1517, which would be expected. Usually the arch, the port arch on the exhaust port is slightly hotter because it's got those exhaust gases going through it. You can also see that the customer has set up an area of interest on the crown, which is currently showing as 1563. And he's also monitoring an area here which he thinks may be a crack between the crown and the walls. And that's significantly cooler at 1478. Mm-hmm. So, again, new ports. This is a cross-fired tank. New ports, very well defined, nice clean edges, good refractory materials, never been used yet. Here's a tank that has just been brought down for a reline. And in this tank, you can see the damage that's occurred around the ports and how the refractory has melted and in some cases cracked away from the port arches and fallen. Okay, and by monitoring these temperatures very accurately, you can time your reversals and tune your burners so that you don't exceed critical temperatures on the refractory, and so you extend the life of the tank itself. Some years ago, tank lives were expected as less than 10 years, and now a lot of people are wanting 15-year tank lives or longer. So it's important to be more careful in monitoring and monitor in the same way every time. The other thing, too, is that if you're getting damage to ports by going over temperature, you may also be getting damage in the regenerative brickwork. And this can result in slumping. So in slumping, you will lose the efficiency of flow through there, and your flames will not propagate as far. The second thing, too, is that if this brickwork glazes, then the brickwork is not as efficient as at absorbing and emitting the energy. Okay, and it becomes less efficient. So again, by monitoring the exhaust sides of these ports, you can protect not just the ports themselves, but the brickwork behind them. This is a Crossfire furnace at another company. Okay, and here, this is during reversal. There's no flames present. Okay, but you can see from these cold ports on this side, this was the side that was just being fired from. And because this is hotter over here, this was the side that was the exhaust side. And in a few moments, it will start to fire from this side across to here. The customer was, in this particular case, also interested in not just crown temperatures, but also the temperature of the melt itself, and also visualizing where that melt line occurred, so that the glass was fully homogeneous by a certain point. So this 1 micrometer, very short wavelength, near-infrared thermal imager provides very high accuracy temperature measurements for the different materials you find within a glass melt tank, whether it's the glass itself or the unmelted batch or the refractory brickwork within the tank itself. Again, very wide field of view, so you're able to see a lot of information within this view. You're able to check refractory temperatures. You're able to select different color palettes or black and white. You're able to set alarms in the system so that if anything goes below a certain temperature or above a certain temperature, it's alarmed. Okay, and by doing all of this, you're able to improve the efficiency of the glass tank and its life. The other comment we've had from a lot of users of this system to date is that the image quality, even though this is a thermal imaging camera, the image quality is actually better than the visual video cameras that they're currently using. And so when a customer buys one of our devices, they usually replace the visual video camera with our thermal imaging camera. And not only do they then get temperature measurements at any point within the scene, but they also get better quality images of what is happening inside the tank. So that's very important. And we've had now 3 years of experience during our phase 1 installations around the world. And this 3 years of experience has really enabled us to understand the environments, what our customers are requiring, the challenges of materials and installation methods as well, so that we are getting trouble-free installations that last a long time, are easy to maintain, and to give very, very good measurements. If you're in the glass container industry, you may be aware that within the glass container industry, 70% of the cost of the container is the energy used to produce that container. Okay, so that's a very important thing. If you can reduce the cost of energy being used in your process, you improve the profit on every container you produce. And by using a thermal imaging device like this, and having a scene which is constructed of over 300,000 temperature measuring pixels, you're able to balance the furnace, you're able to see developing problems, you're able to tune your burners and get better energy efficiency. The other thing too is it helps you currently with the increasing requirements for emissions and carbon emissions. And so again, it helps you to achieve the standards that you are being held to nowadays. So this is what we provide. Here is the what we call the NIR-B glass thermal imaging camera. It has a long lens probe on the face of it. This lens probe is nickel-free. It is coated in high-temperature ceramic, and it is mountable on an optional auto-retraction mechanism such that it will automatically protect itself if somebody was to accidentally turn off coolant or air purge. This thing would automatically retract. If the lens tip for some reason went over a certain critical temperature, it would automatically retract. So it's a trouble-free installation and a very good installation for our customers. So in our phase 1 installations, we've learned a lot about the materials that are necessary for very long life and trouble-free life. Okay, and this ability to have a high-resolution scene with over 300,000 temperature measuring pixels, it is a big advantage now from going from just visual video images now to fully thermal radiometric thermal images to give you better production and longer tank life. So what I'm going to do now is I am going to open up the phone lines so that anybody who has a question can ask. Okay, so I'm going to just unmute everyone.